We'll simplify the expression step by step and highlight the key cancellations as visual cues. The expression is, open parenthesis, 1 minus 1 over x squared, close parenthesis, divided by, open parenthesis, 1 plus 1 over x, close parenthesis. Step 1. Rewrite each part as a single fraction. For the left part, 1 is x squared over x squared, so 1 minus 1 over x squared becomes x squared over x squared minus 1 over x squared, which is x squared minus 1 over x squared. For the right part, 1 is x over x, so 1 plus 1 over x becomes x over x plus 1 over x, which is x plus 1 over x. Now the original expression becomes the fraction x squared minus 1 over x squared, divided by the fraction x plus 1 over x. Step 2. Factor the numerator x squared minus 1 as a difference of squares. X squared minus 1 equals x minus 1 times x plus 1. Step 3. Change division to multiplication by the reciprocal. We multiply by x over x plus 1. Step 4. Cancel the common factor x plus 1 from numerator and denominator. After cancellation, we get x minus 1 times x over x squared. Step 5. Simplify the remaining x terms. Write it as x minus 1 times x over x squared. X over x squared equals 1 over x. So the result is x minus 1 over x. Important domain note. This simplification is valid when x is not 0 and x is not plus or minus 1. Summary. Rewrite as single fractions, factor the numerator, multiply by the reciprocal, cancel the common factor, and simplify the x terms to finish. We will find the value of a and then the other root with a crisp step-by-step plan. Step 1. Plug in the known root to solve for a. Compute each part carefully. Combine constants. Move terms to isolate a. Divide to get the value of a. Step 2. Substitute at equals -1 back into the equation. To make it easier, multiply both sides by -1 to get a positive leading coefficient. Step 3. Use Vieta's formulas for a fast visual cue. For a monic quadratic, the sum of the roots is the positive 6, and the product is 5. We already know one root is 5, so 5 plus the second root equals 6, giving the second root as 1. Final answer, a equals -1, and the other root is 1. We will go step by step and use a sign chart as a fast visual cue. Step 1. Factor the numerator and the denominator. The numerator x squared minus 4 is x minus 2 times x plus 2. The denominator x squared plus x minus 6 is x minus 2 times x plus 3. Put these into the inequality. Important domain note. The common factor x minus 2 is in the denominator, so x equals 2 makes the expression undefined and must be excluded. We may simplify to x plus 2 over x plus 3, but we must carry the restriction x not equal to 2. Step 2. Find all critical points. Zeros of the numerator occur at x equal -2 and at x equal 2. Zeros of the denominator occur at x equal -3 and at x equal 2. List them in order, -3, -2, and 2. Remember, x equals 2 is excluded because the denominator is 0 there.
Using a quick centering trick that makes the algebra collapse nicely. Step 1. We want all solutions, real or complex, of this equation. Step 2. Center the variable around the middle point 2. Let t equal x minus 2. Then x equals t plus 2. That turns the 3 shifts into t plus 1, t, and t minus 1. Substituting gives the new equation. Left side becomes open parenthesis t plus 1 close parenthesis cubed plus t cubed plus open parenthesis t minus 1 close parenthesis cubed equals 0. Step 3. Expand each cube. T plus 1 cubed equals t cubed plus 3t squared plus 3t plus 1. T cubed is just t cubed. T minus 1 cubed equals t cubed minus 3t squared plus 3t minus 1. Step 4. Add all 3 expanded lines. We get t cubed plus 3t squared plus 3t plus 1 plus t cubed minus 3t squared plus 3t minus 1. The plus 3t squared and the minus 3t squared cancel. The constants 1 and minus 1 cancel. We are left with 3t cubed plus 6t. Step 5. Factor out the common factor. 3t times t squared plus 2 equals 0. So either t equals 0 or t squared plus 2 equals 0. Solve the branches. From t equals 0, we already have t equals 0. From t squared plus 2 equals 0, t squared equals negative 2, so t equals plus or minus I times square root of 2. Now convert back to x using x equals t plus 2. Therefore, the three solutions are x equals 2, x equals 2 plus I times square root of 2, and x equals 2 minus I times square root of 2. Only x equals 2 is real. The other two form a complex conjugate pair. Quick visual cue. Center at 2, so the shifts become t plus 1, t, and t minus 1. The quadratic parts cancel, leaving 3t cubed plus 6t. Factor to 3t times t squared plus 2, and solve. Shift back by 2. Done. X to the fourth plus x squared plus 1, using a clean, visual, step-by-step method. Every line you see will match the narration exactly. Step 1. Recognize a hidden connection to x to the sixth minus 1. Write x to the sixth minus 1 as open parenthesis x squared close parenthesis cubed minus 1 cubed. This equals x squared minus 1 times x to the fourth plus x squared plus 1. Therefore, our target equals the fraction x to the sixth minus 1 over x squared minus 1. Step 2. Factor x to the sixth minus 1 completely. First, as a difference of squares of cubes, x to the sixth minus 1 equals x cubed minus 1 times x cubed plus 1. Now factor each cubic. X cubed minus 1 equals x minus 1 times x squared plus x plus 1. And x cubed plus 1 equals x plus 1 times x squared minus x plus 1. Putting it all together, we get 4 factors in a row. Step 3. Cancel the common factor x squared minus 1. We also know x squared minus 1 equals x minus 1 times x plus 1. Since x to the sixth minus 1 equals x squared minus 1 times our target. And we also factored x to the sixth minus 1 into those 4 factors. The remaining factor must be exactly x squared plus x plus 1 times x squared minus x plus 1. Quick check. The product should expand back to our quartic. Start with the product. Multiply and collect like terms x to the fourth minus x cubed plus x squared plus x cubed minus x squared plus x squared minus x plus 1. The plus x cubed and minus x cubed cancel. The plus x and minus x cancel. For the squared terms, x squared minus x squared plus x squared leaves just 1x squared. So the result is exactly x to the fourth plus x squared plus 1. Final answer. X to the fourth plus x squared plus 1 equals x squared plus x plus 1 times x squared minus x plus 1. Done.
Given that a squared plus a plus 1 equals 0, our goal is a quick, visual, step-by-step solution. Start with the given equation. We will turn it into a power cycle fact. Multiply both sides by the factor a minus 1. That gives left parenthesis a minus 1 right parenthesis times left parenthesis a squared plus a plus 1 right parenthesis equals 0. The product is a cubed minus 1 equals 0, so a cubed equals 1. Since it does not equal 1, this means a is a cube root of unity and powers repeat every 3. Now reduce the exponents modulo 3. 2024 equals 3 times 674 plus 2, so a to the 2024th equals a squared. 2025 equals 3 times 675 plus 0, so a to the 2025th equals 1. So the requested sum becomes a squared plus 1. Use the original relation a squared plus a plus 1 equals 0 to replace a squared plus 1. From a squared plus a plus 1 equals 0, we get a squared plus 1 equals negative a. Substitute that into the sum. Final answer, negative a.
Using the factorization of a squared minus b squared. Step 1. Write a squared minus b squared as a product. A squared minus b squared equals 24. That factors into a minus b times a plus b equals 24. Let the smaller factor be d equals a minus b, and the larger factor be e equals a plus b. Step 2. List all positive factor pairs of 24 for d times e. We show them all in a grid. Step 3. Enforce the parity condition. Since it equals d plus e over 2, and b equals e minus d over 2, d and e must have the same parity so that d plus e and e minus d are even. Bring our pairs back into focus. Cross out the pairs that are not same parity. Keep only the even pairs. Step 4. Solve for a and b from each even pair. First, d equals 2 and e equals 12. Then, a equals 2 plus 12 over 2 equals 7, and b equals 12 minus 2 over 2 equals 5. Valid. Next, d equals 4 and e equals 6. Then, a equals 4 plus 6 over 2 equals 5, and b equals 6 minus 4 over 2 equals 1. Valid. Now, d equals 6 and e equals 4. Then it equals 5, but b equals 4 minus 6 over 2 equals negative 1, which is not positive. Reject. Finally, d equals 12 and e equals 2. Then it equals 7, but b equals 2 minus 12 over 2 equals negative 5, which is not positive. Reject. Step 5. Collect the positive integer solutions. The valid ordered pairs are a equals 7, b equals 5, or at equals 5, b equals 1. Quick check. 7 squared minus 5 squared equals 49 minus 25 equals 24. And 5 squared minus 1 squared equals 25 minus 1 equals 24. Square root of 3x minus 5 equals 1 plus square root of 2x minus 6. Step 1. Set the domain from each square root being defined. 3x minus 5 is greater than or equal to 0, so x is greater than or equal to 5 over 3. 2x minus 6 is greater than or equal to 0, so x is greater than or equal to 3. Therefore, the domain we must check is x greater than or equal to 3. Step 2. Isolate and square once. Move the right radical to the left. Square root of 3x minus 5 minus square root of 2x minus 6 equals 1. Now, square both sides. Use the pattern a minus b squared equals a squared minus 2ab plus b squared. Combine like terms to get 5x minus 11 minus 2 times the square root of the product 3x minus 5 times 2x minus 6 equals 1. Isolate the remaining radical and divide by negative 2. Step 3. Square again to remove the last radical. Square both sides. Clear the denominator by multiplying by 4. Expand left and right sides. Set them equal and collect like terms. We arrive at the quadratic equation x squared minus 8x plus 24 equals 0. Step 4. Use the discriminate. For it equals 1, b equals negative 8, and c equals 24. The discriminate is b squared minus 4ac. That equals 64 minus 96, which is negative 32, less than 0. Therefore, the quadratic has no real roots, so the original radical equation has no real solution in the domain x greater than or equal to 3. The two equations are x squared plus y squared equals 25, and x minus y equals 7. We will use substitution. First, isolate y from the second equation. From x minus y equals 7, y equals x minus 7. Substitute x minus 7 in place of y in the first equation. We get x squared plus parenthesis x minus 7 close parenthesis squared equals 25. Now expand the square. Parenthesis x minus 7 close parenthesis squared equals x squared minus 14x plus 49. Replace it back into the equation. Combine like terms. 2x squared minus 14x plus 49 equals 25. Subtract 25 from both sides. Divide everything by 2 to simplify. Factor the quadratic. We want two numbers that multiply to 12 and add to -7. Those numbers are -3 and -4. So the factorization is parenthesis x minus 3 close parenthesis times parenthesis x minus 4 close parenthesis equals 0. Set each factor to 0. X minus 3 equals 0 gives x equals 3. X minus 4 equals 0 gives x equals 4. Now use y equals x minus 7. When x equals 3, y equals 3 minus 7, which is -4. When x equals 4, y equals 4 minus 7, which is -3. Quick check in the first equation. 3 squared plus -4 squared equals 9 plus 16 equals 25. 4 squared plus -3 squared equals 16 plus 9 equals 25. Both pairs satisfy the circle equation. Therefore, the solutions are left parenthesis 3, -4 right parenthesis, and left parenthesis 4, -3 right parenthesis. Solving and back substituting. Step 1. Write the original equation. Notice that 2 to the 2x equals the square of 2 to the x. Step 2. Use substitution. Let y equal 2 to the x. Then the equation becomes y squared minus y equals 12. Step 3. Move everything to one side to get standard quadratic form. Subtract 12 from both sides. Step 4. Factor the quadratic. We need two numbers whose product is -12 and whose sum is -1. Those numbers are -4 and +3. Step 5. Set each factor equal to 0 and solve for y. From y minus 4 equals 0, y equals 4. From y plus 3 equals 0, y equals -3. Step 6. Reject extraneous values. Since 2 to the x is always positive, y cannot be -3. Step 7. Back substitute. Y equals 4 to solve for x. 2 to the x equals 4. Write 4 as 2 squared. Therefore, x equals 2. Final answer, 2.
We will solve two exponential equations step by step using clear algebraic moves. First, we solve 4 to the power x minus 2 equals 40. Then, we solve 4 to the power x plus 4 to the power x equals 16. Problem A. 4 to the power x minus 2 equals 40. Step 1. Since the variable is in the exponent, take the natural log of both sides. Step 2. Use the power rule of logarithms. The exponent multiplies in front. Step 3. Solve for x minus 2 by dividing both sides by natural log of 4. Step 4. Isolate x by adding 2 to both sides. Step 5. Optional decimal approximation. Compute the natural log values and the quotient. Step 6. Final answers in exact and approximate form. Problem B. 4 to the power x plus 4 to the power x equals 16. Step 1. Combine like terms on the left. 2 copies of 4 to the x makes 2 times 4 to the x. Step 2. Isolate 4 to the x by dividing both sides by 2. Step 3. Rewrite both sides with the same base. 4 equals 2 squared and 8 equals 2 cubed. Substitute. Step 4. Thanks for watching Myverse Maths. If this helped you, hit that like button, drop a comment, share it with your friends, and don't forget to subscribe for more quick maths tricks and proofs.
We will solve the exponential equation step by step using thick text on a black background. The equation is 4 to the power x minus 2 equals 40. Step 1. Recognize that the unknown x is in the exponent, so logarithms will help. Step 2. Take the natural log of both sides. Step 3. Use the power rule for logarithms. The natural log of a to the b equals b times the natural log of a, so we bring x minus 2 in front. Step 4. Solve for x minus 2 by dividing both sides by natural log of 4. Step 5. Add 2 to both sides to isolate x. Step 6. Compute a decimal approximation. Natural log of 40 is approximately 3.6889, and natural log of 4 is approximately 1.3863. Their ratio is approximately 2.6610. Therefore, x is approximately 2 plus 2.6610, which is 4.6610. Step 7. State the exact and approximate answers, and perform a quick consistency check. Exact form x equals 2 plus natural log of 40 over natural log of 4. Approximate value x is about 4.6610. Quick check. 4 to the power x minus 2 equals e to the power natural log 4 times x minus 2, which equals e to the power natural log 40, which is 40. This confirms our steps. Solved completely. Exact and approximate solutions shown.
Thanks for watching Myverse Maths. If this helped you, hit that like button, drop a comment, share it with your friends, and don't forget to subscribe for more quick maths tricks and proofs.
We will solve the equation log base 2 of x minus log base 2 of square root of x minus 1 equals 2. We will proceed step by step, ensure the domain is valid, and finish with a simple, real solution. Step 1. Combine the difference of logarithms using the property. Log base 2 of a minus log base 2 of b equals log base 2 of a over b. So we get log base 2 of x over square root of x minus 1 equals 2. Step 2. Exponentiate to remove the logarithm. If log base 2 of m equals 2, then m equals 2 squared, which is 4. Therefore, x over square root of x minus 1 equals 4. Step 3. Clear the denominator by multiplying both sides by square root of x minus 1. We get x equals 4 times square root of x minus 1. So x equals 4 times square root of x minus 4. Step 4. Substitute t equals square root of x with t greater than or equal to 0. Then x equals t squared. Substitute to get t squared equals 4t minus 4. Bring all terms to one side. T squared minus 4t plus 4 equals 0. Step 5. Factor the left-hand side as a perfect square. T squared minus 4t plus 4 equals t minus 2 quantity squared. Set it equal to 0. T minus 2 equals 0, so t equals 2. Step 6. Back substitute t equals square root of x. Square root of x equals 2, therefore x equals 2 squared, which is 4. Step 7. Domain check for the original logarithms. We need x greater than 0 and square root of x minus 1 greater than 0, which means x greater than 1. Our solution x equals 4 satisfies x greater than 1, and both logarithms are defined and positive inside. No extraneous solutions appear. Therefore, the simple and real solution is x equals 4. We will solve the equation step by step without using the quadratic formula. The equation is parentheses x squared over x squared plus 25, and parentheses squared plus parentheses x squared over x squared minus 25, and parentheses squared equals 30. We will keep the background black and use thick text for clarity. Step 1. Let y equal x squared. This reduces the double square. Then the equation becomes parentheses y over y plus 25, and parentheses squared plus parentheses y over y minus 25, and parentheses squared equals 30. Also note the domain restriction x squared is not equal to 25, so denominators are non-zero. Step 2. Clear denominators. Multiply both sides by parentheses y plus 25 squared times y minus 25 squared. The left side becomes y squared times, parentheses, y minus 25 squared, plus y squared times, parentheses, y plus 25 squared. The right side becomes 30 times, parentheses, y plus 25 squared times, parentheses, y minus 25 squared. Step 3. Expand and simplify. We have y minus 25 squared equals y squared minus 50y plus 625, and y plus 25 squared equals y squared plus 50y plus 625. Adding them inside the brackets gives 2y squared plus 1250. So the left side is 2y to the fourth plus 1250y squared. On the right, note that y plus 25 times y minus 25 equals y squared minus 625. So the right side is 30 times y squared minus 625 squared, which is 30 times y to the fourth minus 1250y squared plus 390,625. Step 4. Bring all terms to one side. We get 28y to the fourth minus 38,750y squared plus 11,718,750 equals 0. Divide everything by 2 to simplify. Step 5. Let u equal y squared. Then we have a true quadratic in u. 14u squared minus 19,375u plus 5,859,375 equals 0. We will factor without using the quadratic formula. We seek integers a and b such that a times b equals 5,859,375, and 7 times b plus 2 times a equals 19,375. Using prime powers of 5, we find a equals 3,125 and b equals 1,875. Indeed, 7 times b plus 2 times equals 13,125 plus 6,250 equals 19,375. Therefore, the factorization is parentheses 7u minus 3,125 and parentheses times parentheses 2u minus 1,875 and parentheses equals 0. Step 6. Solve the factors. 7u minus 3,125 equals 0 gives u equals 3,125 over 7. 2u minus 1,875 equals 0 gives u equals 1,875 over 2. Recall u equals y squared. So y equals the positive square root of u because y equals x squared is non-negative. Then x squared equals y. So x equals plus or minus the square root of y. This yields 4 real solutions. Step 7. Domain check and simple real form. We must have x squared not equal to 25. Our y values are approximately 21.12 and 30.61, so neither equals 25, and the denominators are non-zero. For a simple real summary, the solutions are approximately plus or minus 4.596 and plus or minus 5.534. Final answer, 4 real solutions. We will solve step by step for real numbers x and y such that x plus y equals 4 and x cubed plus y cubed equals 28. Step 1. Write down the system we want to solve. Our two equations are x plus y equals 4 and x cubed plus y cubed equals 28. Step 2. Use the identity for the sum of cubes. X cubed plus y cubed equals the quantity x plus y cubed minus 3xy times the quantity x plus y. Since x plus y equals 4, substitute that into the identity. We get x cubed plus y cubed equals 4 cubed minus 3xy times 4. That simplifies to x cubed plus y cubed equals 64 minus 12xy. But we also know that x cubed plus y cubed equals 28. So set 64 minus 12x, y equal to 28. Step 3. Solve for the product x, y. Move 28 to the left side to get 64 minus 28 equals 12xy. So 36 equals 12xy, which gives xy equals 3. Step 4. Use the fact that x and y are roots of a monic quadratic with sum and product. The general form is t squared minus the sum times t plus the product equals 0. Substituting the values, we get t squared minus 4t plus 3 equals 0. Step 5. Factor the quadratic by inspection. Without using the quadratic formula, we need two numbers that multiply to 3 and add to 4. Those are 1 and 3. So the factorization is t minus 1 times t minus 3, which gives the roots t equals 1 or t equals 3. Step 6. Since x and y are the two roots, the ordered pairs are 1, 3 or 3, 1. We can quickly check both conditions. Each pair adds to 4, and the cubes sum to 28. Both checks succeed. Final simple and real solutions. The ordered pairs are 1, 3 or 3, 1. Solve the system of equations for positive integers x and y. The system is x cubed minus y cubed equals 91, and x minus y equals 1. We'll proceed step by step using factoring and substitution, and end with a simple, real solution. Recall the factorization of a difference of cubes. X cubed minus y cubed equals, open parenthesis, x minus y, close parenthesis, times x squared plus x, y plus y squared. Because x minus y equals 1, the first equation becomes x squared plus xy plus y squared equals 91. From x minus y equals 1, we have x equals y plus 1. Substitute this into x squared plus x, y plus y squared equals 91. That gives, open parenthesis, y plus 1 close parenthesis squared, plus y times open parenthesis, y plus 1 close parenthesis, plus y squared equals 91. Expand each term. We get y squared plus 2y plus 1, then plus y squared plus y, then plus y squared equals 91. Combine like terms to get 3y squared plus 3, y plus 1 equals 91. Subtract 91 from both sides. 3y squared plus 3, y minus 90 equals 0. Divide everything by 3. Y squared plus y minus 30 equals 0. Factor the quadratic without using the quadratic formula. We need two integers whose product is negative 30 and whose sum is 1. Consider factor pairs of 30. 1 and 30, 2 and 15, 3 and 10, 5 and 6. To get a sum of positive 1 with product negative, we choose plus 6 and minus 5. Therefore, y squared plus y minus 30 factors as open parenthesis, y plus 6 close parenthesis times open parenthesis, y minus 5 close parenthesis equals 0. Set each factor equal to 0. We get y equals negative 6 or y equals 5. Since we want positive integers, we take y equals 5. Use x equals y plus 1. With y equals 5, x equals 6. Let's verify both equations. 6 cubed minus 5 cubed equals 91, and 6 minus 5 equals 1. Therefore, the unique positive integer solution is x equals 6 and y equals 5.
We are asked to find the two-digit number that equals 3 times the sum of its digits. Let's model the number with a tens digit and a ones digit, and then write an equation. Step 1. Let the tens digit be t and the ones digit be u. A two-digit number with tens digit t and ones digit u is 10t plus u. Step 2. The problem says the number equals 3 times the sum of its digits. That is, 10t plus u equals 3 times the quantity t plus u. Step 3. Expand and collect like terms. On the right we have 3t plus 3u. Move terms to one side to get 7t minus 2u equals 0, which is the same as 7t equals 2u. Step 4. Digits have limited values. The tens digit t is between 1 and 9, and the ones digit u is between 0 and 9. From 7t equals 2u, we can write u equals 7 halves times t. For u to be an integer, t must be even. Let's test even tens digits. T equals 2, t equals 4, t equals 6, and t equals 8. For t equals 2, u equals 7. That is a valid digit. For t equals 4, u equals 14, too big. For t equals 6, u equals 21, too big. For t equals 8, u equals 28, too big. So the only valid pair is t equals 2 and u equals 7. Step 5. Therefore t equals 2 and u equals 7, so the number is 27. Let's check. 3 times the sum of its digits is 3 times the quantity 2 plus 7, which equals 3 times 9, or 27. The condition is satisfied. Final answer, 27.
In this video, we will solve the following system step by step, with no step skipped. We want positive integers, a, b, c such that a plus b plus c equals 12, ab plus bc plus c a equals 44, and abc equals 48. We will use the idea of building a monic cubic polynomial whose roots are a, b, and c. If a, b, and c are roots of a monic cubic, then by Vieta's formulas the polynomial is x cubed minus the sum times x squared plus the sum of pairwise products times x minus the product equals 0. Substitute the given values to get our exact cubic equation. Now, we find integer roots using the rational root theorem. Possible integer roots are plus or minus divisors of 48. That is 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. We test small positive candidates first because a, b, c are positive. Compute f of 1. 1 minus 12 plus 44 minus 48 equals negative 15, not 0. Now compute f of 2. 2 cubed is 8, minus 12 times 2 squared is minus 48, plus 44 times 2 is plus 88, minus 48 gives 0. So x equals 2 is a root. We factor out x minus 2 using synthetic division. Write the coefficients. 1, negative 12, 44, negative 48. Bring down the 1. Multiply 1 by 2 to get 2, add to negative 12 to get negative 10. Multiply negative 10 by 2 to get negative 20, add to 44 to get 24. Multiply 24 by 2 to get 48, add to negative 48 to get 0 remainder. So the quotient is x squared minus 10x plus 24. Now solve x squared minus 10x plus 24 equals 0. We need two numbers that multiply to 24 and add to 10. List factor pairs of 24. 1 and 24, 2 and 12, 3 and 8, 4 and 6. Only 4 and 6 add to 10. Therefore, the quadratic factors as left parenthesis x minus 4 right parenthesis times left parenthesis x minus 6 right parenthesis equals 0. So the remaining roots are x equals 4 and x equals 6, together with the root x equals 2 that we already found. The three roots are 2, 4, and 6. Since a, b, and c are the roots, the solution set of positive integers is a, b, c equals 2, for 6 in some order. We can present the triple as 2, 4, 6. We verify each original equation explicitly. Sum check. 2 plus 4 plus 6 equals 12. Pairwise products. 2 times 4 plus 4 times 6 plus 6 times 2 equals 8 plus 24 plus 12, which equals 44. Product check. 2 times 4 times 6 equals 48. All conditions are satisfied. Final answer. The positive integer triple is 2, 4, and 6 in any order. We use Vieta's formulas to build a cubic, rational root theorem to find a root, synthetic division to reduce to a quadratic, then factored the quadratic, and verified all conditions step by step.
Today we're going to solve a system of equations problem. We have two positive integers x and y that satisfy two conditions. X plus y equals 25, and x times y equals 144. Our goal is to find the values of x and y. Step 1. Let's express one variable in terms of the other. From the first equation, x plus y equals 25, we can solve for y. We get y equals 25 minus x. Step 2. Now, we substitute this expression for y into the product equation. We have x times the quantity 25 minus x equals 144. Step 3. Let's expand and collect terms to form a quadratic polynomial. Expanding gives us 25x minus x squared equals 144. Rearranging all terms to one side, we get negative x squared plus 25x minus 144 equals 0. Step 4. Now we need to factor the quadratic. We're looking for two integers whose product is 144 and whose sum is 25. Let's list the factor pairs of 144 and find their sums. Notice that 9 times 16 equals 144 and 9 plus 16 equals 25. This pair works. So the factors are negative 9 and negative 16. Step 5. Using the zero product property, we set each factor to 0. X minus 9 equals 0, or x minus 16 equals 0. Step 6. Solving these equations, we find x equals 9 or x equals 16. Now, we need to find the corresponding y values using our equation y equals 25 minus x. If x equals 9, then y equals 25 minus 9, which equals 16. If x equals 16, then y equals 25 minus 16, which equals 9. Step 7. Let's verify that these pairs satisfy both original equations. For both pairs, x plus y equals 25, and x times y equals 144. Both conditions are satisfied. Therefore, our final answer is the pair x equals 9 and y equals 16, or equivalently, x equals 16 and y equals 9. Both represent the same solution to our system of equations. Let's visualize our solution. We can represent this problem as finding two numbers that fit in a rectangle. The two numbers are the dimensions, their sum is the semiperimeter, and their product is the area. Our solution shows that a rectangle with dimensions 9 by 16 has a semiperimeter of 25 and an area of 144. In this problem, we learned how to solve a system of equations by substitution, factoring a quadratic, and verifying our solution. The key insight was recognizing that we needed to find factor pairs of 144 that sum to 25. Thank you for watching.